Welcome to the deep dive. Today we're digging into a really interesting paper from Hugging Face and Stanford University. It's called SmolVLM, Redefining Small and Efficient Multimodal Models.
Yeah, this one caught my eye too. It tackles a big problem, right? Vision language models are getting incredibly powerful, but they're also, well, huge and compute hungry.
Exactly. Especially if you want to run them on, say, a phone or some edge device. It's just not feasible most of the time. So this paper asks, can we get great multimodal performance without needing a supercomputer?
And spoiler alert, their answer seems to be a resounding yes.
Right. So for a quick snapshot, SmolVLM delivers surprisingly strong results on both image and video tasks. And get this, the smallest version runs on less than a single gigabyte of GPU RAM.
Less than a gig? That's tiny in the VLM world.
It really is. And it actually outperforms much older, larger models and benchmarks. They also show it's got solid video understanding chops even on edge hardware.
Which points to some clever design choices. It's not just about shrinking things down, is it? It's about optimizing the architecture, being smart about tokens, picking the right training data.
Precisely. Yeah. So our mission today is to unpack how they did it. What are the architectural tricks, the training strategies that let SmolVLM punch so far above its, well, small weight class?
Yeah, let's get into the nitty-gritty. It's a compelling counterpoint to the bigger is always better trend we've seen for so long. What's the minimum size for a really capable multimodal model? That's the key question here.
Okay, so let's start with the architecture itself. Figure 2 in the paper lays it out. It begins with the visual input, right? Images get split up, videos get frame sampled.
Yep, standard stuff so far. Images are broken into sub-images, and for video, they just sample frames. These visual bits then go into a vision encoder. They use SIGLIP here to pull out the features.
Okay, feature extraction. Then what?
Then comes a neat trick, a pixel shuffle operation. Instead of just passing the features along, they kind of rearrange the spatial information into the feature channels.
Rearrange. How does that work?
Think of it like taking a grid of features and swishing the spatial dimensions, width and height, partly into the depth or channel dimension. It makes the representation denser per token, but reduces the total number of tokens.
Okay, so fewer tokens, denser information within each, then they project these shuffled features.
Right. An MLP projection maps these rearranged visual features into the language model's input space, turning them into visual tokens.
Gotcha. And these visual tokens then get combined with any text input.
Exactly. They're concatenated or interleaved with the text embeddings, and the whole sequence text and visual tokens together goes into their SmolLM2 language model backbone to generate the text output. It's a pipeline really optimized for handling visual info efficiently within an LLM framework.
Sounds intricate. Now, one really critical part mentioned in section 2.1 is how they balance the compute between that vision encoder, SIGLIP, and the language model, SmolLM2. They played around with different sizes.
Yeah, this is super important. They tested 3 sizes of SmolLM to 135 million, 360 million, and 1.7 billion parameters, and paired each with 2 different SIGLIP encoders, a smaller 93 million parameter one and a larger 428 million one.
And what did they find? Just use the biggest of both?
Well, that's what you might intuitively think, but no. Especially not for the smaller end. When they paired the largest vision encoder with the smallest language model, the 135M1 performance actually went down.
Really? Why?
It seems like it created an imbalance. The small LM just couldn't effectively process all their rich information coming from the big encoder. It was overwhelmed, basically.
Huh. So a balanced diet is key for these small models.
Exactly. For the middle 360M language model, the larger encoder did give a performance boost, about 11.6%. But it also increased the total model size by 66%.
Oof, that's a big jump in parameters for that level of improvement. Probably not worth it for efficiency.
Right. So for that size, the smaller encoder was the more practical choice. It was only when they got to the largest 1.7 billion parameter language model that the bigger vision encoder made more sense. It offered a good performance bump for only a 10% increase in total parameters.
Okay, so the takeaway is balance is crucial. And for smaller VLMs, leaning towards a relatively smaller, efficient vision encoder is often the better strategy.
Precisely. You need the parts to work well together within the resource budget.
Makes sense. Okay, moving on. Section 2.2 tackles getting those visual tokens into the language model efficiently. They use self-attention, which we know can get heavy with lots of tokens. And high-res images mean lots of tokens.
Yeah, that's the bottleneck. A standard 512 by 12 image processed by their smaller SIGLIP encoder already spits out over 1,000 visual tokens. Their SmolMN2 initially had only a 2K token context window.
So you could barely fit one decent image in there, let alone text or multiple images or video frames. How did they fix that?
They had to extend the context capacity. They did this mainly by tweaking rotary position embedding. They cranked up the Ropey base value significantly, from 10K to 273K, which helps the model handle longer sequences.
Just changing a number makes it work for longer sequences?
Well, it gives the architecture the ability to handle longer sequences, but then you have to train it to actually use that ability. So they fine-tuned the models on a mix of data-long documents like books, code from the stack, but also shorter stuff like web text and math problems.
So the bigger Ropey base provides the space, and the mixed training teaches the model how to navigate it.
You got it. And I found something interesting during this fine-tuning. Their largest 1.7B model was stable training up to 16,000 tokens.
Oh, that's a big jump from 2K.
Huge jump. But the smaller models, the 135M and 360M ones, started to struggle beyond 8,000 tokens. Training became unstable.
Ah, okay. So there are still limits depending on the model size.
Right. So the final small VLM models ended up with a 16K context window, while the smaller variants use an 8K window. Still, a massive improvement over the original 2K and clearly vital for making these compact models truly capable with visual inputs.
Definitely. More context helps understand the bigger picture or more details. Now let's circle back to that pixel shuffle technique you mentioned. Section 2.2 and Figure 4 go deeper into this visual token compression. Can you unpack that a bit more?
Sure. Pixel shuffle, technically called space to depth, is a clever way to reduce the number of visual tokens you feed into the LLM. Remember, attention complexity grows quadratically with sequence length, so fewer tokens is generally good.
Okay, how does it reduce the tokens again?
Imagine you have feature vectors representing patches of the image. Pixel Shuffle takes spatial information from neighboring patches and packs it into the channel dimension of fewer feature vectors. So you end up with fewer tokens overall, but each remaining token carries denser information, effectively covering a larger spatial area but with more feature channels describing it.
And the reduction factor is significant.
Very. If the shuffle ratio is R, the number of tokens goes down by R squared. So if R is 2, you get 4 times fewer tokens. If R is 4, you get 16 times fewer tokens.
16 times. But there must be a downside, right? Doesn't that lose detail?
It can, yes. If you compress too much, you lose fine-grained spatial resolution, which hurts tasks that need precise localization, like reading small text in OCR.
So what ratio did they use?
Well, some bigger models like InternVL use a ratio of 2, but the small VLM team found that their smaller models actually benefited from being more aggressive. They use a ratio of 4.
Why would more compression be better for smaller models? Seems backward.
Their reasoning is that the drastic token reduction, 16x, really helps manage the computational cost of attention, especially within those newly expanded context windows. For these small models, the efficiency gain and the ability to handle longer effective sequences outweighed the slight loss in fine spatial detail for many tasks.
Huh. Interesting trade-off. Prioritize sequence length and compute over absolute spatial fidelity per token. Okay, section 2.3 talks about encoding images versus videos efficiently.
Right, they need different handling. High-res images need detail, meaning potentially lots of tokens. Videos are sequences, so you might want fewer tokens per frame to fit more frames into the context window for temporal understanding.
So how did they handle high-res images without blowing the token budget?
They used image splitting, inspired by models like your reader. Basically, they chop the big image into smaller sub-images, like a grid. They feed these sub-images to the model, along with a downsized version of the whole image to give it global context.
Like focusing on parts but keeping an eye on the whole picture. Smart. What about video? Did they try squishing frames together?
They did. They experimented with frame averaging, combining the features of several consecutive frames into one representation. It's a technique others have used to save compute.
Did it work for small VLM?
Nope. Figure 3 shows it actually hurt performance on video benchmarks, and it got worse the more frames they averaged.
Really?
Any idea why? They don't speculate too much, but maybe averaging just blurs too much temporal detail for these smaller models. Or perhaps the specific way they implemented it wasn't optimal for their architecture. Whatever the reason, they dropped it.
So what did they do for video frames instead?
They just took the sampled frames and rescaled them to the resolution the image encoder expects. Simple, and it worked better than averaging.
Interesting how optimization strategies aren't always transferable, especially across model scales. Okay, that brings us to section 3. Small instruction tuning. Sounds like the data and training setup were crucial.
Absolutely. When your model is small, you have to be extra careful about how you train it and what data you use. Every bit of capacity counts. Section 3.1 has a fascinating story about positional tokens.
Oh yeah, for those sub-images from the image splitting. How do they tell the model where row 1, column 2 was?
Initially, they tried the simplest thing, just using text strings like row 1, col 2. Easy, right?
Seems logical.
But it caused problems. They called it the OCR loss plague. The training loss would suddenly plummet, looking like great progress. But the actual OCR performance wasn't improving at all. The model seemed to be getting stuck, finding some weird shortcut related to those string tokens instead of actually learning to read. Figure 5 shows the training just plateauing.
Yikes. So how did they fix the plague?
They switched to learned positional tokens. Instead of raw text, they created specific embedding vectors that the model learned during training to represent each grid position, row 1, col 1, row 1, col 2, etc.
So the model learns its own internal representation of top left or middle right.
Exactly. And the difference was huge. Training became stable, convergence was much better, and critically, OCR accuracy and performance on other tasks improved significantly.
Wow. And was this more important for the smaller models?
Yes, definitely. Figure 5 clearly shows that while bigger models could kind of cope with the string tokens, the smaller small VLMs got a massive boost from the learned positional ones. It really highlights how these tokenization details matter immensely at smaller scales.
Fascinating. Little details, big impact. Section 3.2 talks about structured prompts and marking where the media is.
Yeah, more on the input formatting. They looked at system prompts, those initial instructions like, you are our helpful assistant, or describe this image.
Do those help?
They found they did, especially for image tasks, as shown in Figure 6. It just gives the model clearer context about what it's supposed to do.
Okay, makes sense. What about marking the media?
They also tried adding special tokens to signal the start and end of visual content, like putting, here is an image, before the image tokens, and maybe given the image after.
Like signposts for the model. Attention. Visual stuff here.
Pretty much. And again, it gave a really noticeable performance boost, especially for video tasks, but also measurably helped on image tasks too. Just explicitly telling the model, this part is visual, seems to help it focus.
Simple but effective. They also mentioned masking user prompts during fine-tuning.
Right. This is about preventing overfitting during the supervised fine-tuning SFT stage. Instead of training the model on both the user's question and the desired answer, they masked out the user's question.
So the model only learns to predict the answer.
Exactly. It forces the model to rely more on the visual information and the learned task, rather than potentially just memorizing common question-answer patterns. Figure 6 shows this improved performance too. Train only on the completions.
Clever. Discourages shortcuts. Now, Section 3.3 hits on something weird. Reusing text data from LLM fine-tuning was actually bad.
Yeah, this one is counterintuitive. They had this data set called Smalltalk from fine-tuning their language models. You'd think adding that high-quality text data to the multimodal training mix would help, right? More language knowledge.
Seems logical,
But Figure 7 shows it actually degraded performance for the small VLM models, up to 6.5% drop on image tasks, 3.7% on video.
Why would good text data hurt?
Their hypothesis is that it reduced data diversity. By reusing that specific LLM text data, they potentially crowded out more varied multimodal examples that might have been more beneficial for learning the vision language connection in these compact models. They found sticking to a strict 14% text proportion in the mix, using new text SFT data, worked better.
So for small VLMs, tailored multimodal data variety trumps reusing generic, even if high-quality LLM text. Interesting. What about chain of thought in 3.4? CoT helps big models reason.
Does it help small ones? That was the question.
Yeah.
They took CoT data from the Mammoth benchmark and tried adding different amounts to their training mix.
And the results?
Very, very minimal amounts, like 0.02% to 0.05% of the data gave a tiny performance bump. Most negligible.
Oh, and more CoT.
Performance dropped.
Significantly.
Especially on image tasks. Figure 7 shows this quite clearly.
So CoT is mostly a no-go for small VLM. Why?
The thinking is that the complex, step-by-step reasoning text in CoT data just takes up too much of the limited capacity of these small models. It might actually detract from their ability to learn and represent the visual side of things effectively. You have to be super careful not to overwhelm the model with purely textual reasoning.
Right, the capacity budget is tight. Need to spend it wisely, focusing on the multimodal aspects. Okay, last tuning point, section 3.5, video length. How long should the training videos be?
They explored this trade-off. Longer videos mean more temporal context, which is good for understanding actions and sequences, but also means more tokens, more compute.
So what's the sweet spot?
They trained using average video lengths from 1.5 up to 3.5 minutes. Figure 7 shows performance improving on both video and image benchmarks as the duration went up towards 3.5 minutes.
Even image benchmarks improve from longer videos.
Yep, suggesting that learning from longer sequences helps the model develop better cross-modal representations generally. But beyond about 3.5 minutes, the gains started to flatten out. The extra compute cost wasn't really justified by the tiny improvements.
So moderately long videos, around 3.5 minutes on average, seemed optimal for training these compact models.
Got it. Okay, so after all that tuning and architectural tweaking, Section 4 introduces the actual small VLM family and shows off the results.
Right, the payoff. There are 3 main versions.
Yep. First, small VLM 256M. This is the super tiny one, under 1 GB of GPU RAM. Uses a small 93M cyclip encoder and the smallest 135M small M2. Perfect for really tight constraints, like basic phones or microcontrollers.
Wow, okay then.
Small VLM 500M, and still small, needs about 1.2 GB RAM. Same small 93M vision encoder, but steps up to the medium 360M language model. A good balance for maybe higher-end mobile or low-power edge devices.
And the biggest small one?
Small VLM 2.2B. This one needs around 4.9 GB of RAM, so still quite efficient compared to giants. It uses the larger 400M cyclip encoder and the 1.7B language model. This one aims for maximum performance while still being edge deployable on more capable hardware.
Okay, 256M, 500M, and 2.2B parameters roughly. How do they actually do on tests?
Table 1 is packed with benchmark results. They tested across tons of stuff. Single image tasks like OCR, diagram understanding, AI2D, chart QA, document VQA, science questions, math reasoning, general visual QA, plus multitask benchmarks like MMMU, and a suite of video benchmarks testing understanding and temporal reasoning.
And the headline, how does small VLM compare?
Amazingly well, especially considering the size. They consistently achieve strong accuracy, often beating models many times larger, while using way less RAM. Figure 1 has that striking comparison where even the tiny small VLM 256M outperforms the massive, 80 billion parameter IDFix model from a couple of years ago on several benchmarks.
That's wild, 256 million parameters beating 80 billion. Shows how far efficiency has come.
It really does. Now, they are honest about limitations. On really complex reasoning tasks like the full MMMU benchmark or AI2D diagrams, bigger language models still have an edge. The linguistic power matters there.
Makes sense. Some tasks just need more language horsepower.
But interestingly, even within the small VLM family, scaling up the language model from 135M to 1.7B did give clear boosts on visually grounded tasks like OCR, so language scale still helps even when visual processing is key.
Okay, and how does the small VLM 2.2B compare to other compact models around the 2 billion parameter mark?
Figure 1 shows it holds its own very well. On tough benchmarks like MathVista and Science QA, it delivers strong results while using significantly less GPU RAM, just under 5 GB, compared to models like Qwen2VL2B or InternVL22B, which can need twice that or more.
So competitive performance at much lower resource cost. What about video?
They seem particularly strong there. Table 1 shows small VLM excelling on video benchmarks like Video MME and WorldSense, again, often outperforming larger models. The 500M variant also showed solid results on temporal reasoning tasks.
Impressive. And did they actually test running these on devices? Section 4.4 mentions on-device performance.
They did. Figure 9 shows throughput tests how many tokens they can generate per second. They tested on high-end A100 GPUs, but also on more modest L4 GPUs, which are more common in edge servers.
And the results were good.
Yeah, very promising. Good scaling on the A100 and respectable speeds even on the L4, confirming they're suitable for edge deployment. Plus, they released optimized ONNX versions, which makes it easier to run them on different types of hardware.
ONNX is definitely helpful for deployment.
And maybe the coolest demo, they got the tiny 256M model running in a web browser using WebGPU.
In the browser. Seriously.
Yep, hitting up to 80 decoded tokens per second on a recent MacBook Pro. That really opens the door for a client-side multimodal AI without needing any back-end servers.
That's huge. True on-device intelligence. Finally, Section 4.5 mentions some real-world uses starting to emerge.
Just briefly, they mention small VLM for general on-device stuff, phones, laptops, browsers. There's small dockling, an ultra-compact version for document processing using something called doc tags, and BioVQA, which is looking at using small VLM for analyzing medical images in low-resource healthcare settings.
So people are already building practical things with it. That's great validation.
Definitely shows the potential impact of making powerful AI this efficient.
Okay, this has been a fantastic deep dive. So wrapping up, the core achievement here is showing you can get powerful multimodal AI without massive compute, right?
Absolutely. Small VLM proves that intelligent, compact design can seriously challenge the scale at all costs approach. It wasn't just shrinking, it was smart architectural choices like balanced encoder-LM sizes, clever token management like pixel shuffle and learned positional tokens, and really careful training strategies, image splitting, optimized data mixes, the right context length, minimal STUT.
A whole suite of targeted optimizations.
Exactly, all working together under tight resource constraints.
And for the AI researchers and ML engineers listening, the big implication is that advanced multimodal AI on edge devices, on your phone, in your browser, it's becoming much more realistic.
For sure. It opens up possibilities for new applications in mobile edge computing, maybe even areas like assistive tech, robotics, specialized fields like healthcare or document analysis where efficiency is critical. And the open sourcing of the models, code, and data is huge for the community.
Yeah, props to them for releasing it all. It lets everyone build on this work. Okay, so final provocative thought for our listeners. SmolVLM tackled specific bottlenecks related to size and compute for VLMs. What are the next big roadblocks? What other fundamental architectural or data challenges exist in multimodal AI that, if solved with similar ingenuity, could unlock even more efficient and maybe even more capable systems? And what totally new applications could we dream up if these efficiency barriers fall even further?
Lots to think about there. Where does efficiency lead us next?
Definitely. Well, thanks for joining us on this deep dive into the impressive work behind SmolVLM.